before I go into some details, can I maybe ask who knows something about consensus, such that I can maybe sometimes skip some parts? Okay, half. Then I can skip, so I will go through all of it. So yeah, the screen is not right. Yeah, the screen is not right. I need to switch. Yeah, so first then I again introduce the problem, then I give a very general framework on how DAG-based consensus works and what are the differences between those. Then we'll talk about uncertified DAGs and what motivated us to work on, say, this topic. And then I'll present the protocol itself, and finally we'll have some comparison, some performance comparison with some other protocols. So the first thing is we consider a typical blockchain problem when we have clients who submit transactions to validators, and the job of validators is just sequence and verify transactions such that they can produce a log of transactions, a sequence of transactions. After that, they can execute, store this, the effects of the transaction, and send back to the client the response that they executed with that effects, and the client can be ensured that he knows what will be the results of the execution. But the focus will be mostly about this part when we sequence and verify transactions, when we sequence. So basically we will look into, so this is just the whole kind of like life cycle of transaction, but we will look on how it works after the transaction landed on some of the validators, and then it ends up in the, say, block, and then it will be sequenced. Yeah, so we will look only on that part. So, and typically when we talk about consensus, we want to provide these two properties, safety and liveness. Safety means that the logs are consistent across all the honest validators, and liveness means that if there is a valid transaction submitted to one of the honest validators, then eventually it will be included in the log of all honest validators.
Sorry, could you maybe stay on the other side?
Yeah.
Thank you very much.
Yeah. So basically what we have here, so we have a network where we have a point-to-point communication. This is pretty important just to provide the lowest possible latency, because if we have, say, gossip network, then it takes a little bit longer to deliver one message from one validator to another. And we assume that each message sent by honest validator to another honest validator is eventually delivered. So that means that we, again, don't have a precise bound on when it will be delivered, but there could be different delays. But, and we don't assume any, we don't assume completely asynchronous communication, so we consider this like practical trade-off between synchronous and asynchronous communication, such that there is a certain moment called global stabilization time, such that before that moment communication is asynchronous and nobody knows about this moment, but after that moment communication gets synchronous with a known delay delta. So, and typically consensus protocols require not only to be safe and live, but also to be fault tolerant, meaning that if some of the validators misbehave arbitrarily, they do what they want, we still can provide all those two properties, safety and liveness. Yeah, and the number of faulty nodes is less than 1/3 of the total number of validators. Okay, now let's go into the framework how consensus works if we employ the DAG structure. So typically what I'm going to do right now I'm going to explain how validators construct the DAG, the directed acyclic graph. So we have validators, so they land on the left side, and they will construct their blocks from left to right. We will proceed in rounds. So now we have kind of like blocks, and each block points not to only one parent, but to multiple ancestors in the previous rounds. So typically you include transactions in the block, you also sign it. So, and there are several rules how most of the DAG-based protocols works, so I will explain. There are many differences between those, but typically we preserve all these rules. So you create one block in each round, and if you create multiple of those, then probably you are not honest validator. Then you don't need to create blocks at your own pace. You need to wait until the network when the quorum of the network is already at the previous round, then you can potentially create a block in the next round. So you should not just be very fast. You should be aligned with the network speed, basically. So yeah, there is a quorum of references to the blocks from the previous round. That's what we have as a rule when we just check the validity of the block. Then another rule is that since we have a DAG structure here, and at the end of the day we want to end up with log or a sequence of blocks, for instance. So we need to linearize all these blocks in the DAG, and the way how typically DAG-based consensus protocols works, they choose leaders in certain rounds. We have this scheduler for leaders, and everybody agrees on this schedule who will be the leader in that round. And these leader blocks that we have here with crowns, they will be used to linearize the causal past of those blocks. So, and the mechanics for that is that we do some voting directly on this DAG. How do we do this? We just again employ the same references that we have, and this voting will be somehow counted, and we will decide whether use this leader block for linearization or not use this block for linearization. And just if you have some local perception of the DAG, then what you're gonna do to sequence all the blocks or sequence some blocks in the local DAG, you first try to commit leader blocks. You want to find which blocks can be committed. So for instance, let's say here these 3 blocks can be committed, and we still don't know whether the block at round 4 can be committed because there is not enough maybe votes so far, or we need to wait for blocks from round 6. So we commit these leaders, and after that, as I said, we need to linearize their past. So we need to traverse from the past committed leaders to the most recent committed leaders, traverse the DAG, and just pick up all the blocks that are not yet traversed. So this is the way how we do it, and the sequence of blocks then derived in this manner. So, and again, as I said, I would say all the DAG-based protocols that we have in the last, say, 4 or 5 years, we do the same thing. So we try to commit leaders, then we want to linearize past. So, but not all the leaders are committed. Sometimes when we say don't have enough votes, so this DAG is a little bit different. And in this case, the leader block at round 2 is not committed because there are not enough votes for this leader block. Yeah, and in this case, we just do the same. We commit leaders. If the leader can be committed, so D2 is not committed, then we don't use it for traversing. And that way, everybody, so first everybody learns which leader blocks can be committed, and then we can linearize the past. And basically, all DAG-based protocols are doing the same thing here. So let me now point some difference between two directions for the DAG. So typically there are so-called certified DAGs. One of the examples could be Aleph, Bullshark, and uncertified DAGs. The difference is that how we ensure that the block can be added to our local DAG. So in certified DAGs, the way how it's done is through so-called certificates. So basically, if you create a block, the first thing you do is you multicast that block to every other validator, and every other validator basically receives this block, and if it's the first block from that validator in that round, if it's all valid, then they send back the signature, and the block creator then aggregates signatures and send back to everybody else the certificate for this block. So a quorum of signatures, and this way you ensure that the block can be added to the local DAG. It's available on the quorum of the network. It's unique. Yeah, but and this is completely different to the concept of uncertified DAGs, where every block is sent through using best effort manner, and you add the block optimistically without checking that it's available and it's unique. And this kind of like a trade-off between the way at which speed we construct the DAG, and maybe it will result into latency. On the other hand, we can talk about some there could be more attacks on uncertified DAGs, because there could be equivocations, because for instance here say guy D in round 3 created 2 equivocating blocks, and it could send one block to one guy, another block to another guy. They checked these blocks are correct. We have the whole past, and they integrated that blocks to the local DAG, and they built their blocks on top of that. But the good thing about uncertified DAGs is that it can result in much smaller latency, because you produce blocks more frequently. So specifically, if you also talk about like end-to-end latency, say we receive some transaction, one of the validators receives this transaction, then it takes, again, also a little bit shorter time just to include the transaction in the block. So this kind of like the time to include the transaction is much shorter for uncertified DAGs. So, and yeah, let's now talk a little bit, amplify the problems that we have with uncertified DAGs. So in theory, when you create a new block in uncertified DAG, then the way how you have to disseminate your blocks is send your block, and in addition, you need to send some potential ancestors of your blocks, such that the receiver can immediately integrate your block in the local DAG. Otherwise, they might have some problems. For instance, here, let's say we are playing a role of validator A, and we created a block A6, and we are now thinking we are going to send our block to validator D, the last one. Since we don't know yet that the validator D has its blocks B5 and C5, we have to send them to validator D, because if it doesn't have those blocks, then it will not be able to integrate our block A6 in its local DAG. That's the basic logic behind. But as you can see, with this approach, almost every block has to be communicated between almost every pair of validators, and it leads to a quadratic complexity of communication even for transaction data. So what's done in implementation and Mysticity, one of the examples how cordial miners is implemented. We do just so-called pool strategy. It's like more practical because you send only your block, and if the receiver doesn't have some of the ancestors, then it will pull and ask, okay, please send me that ancestor, and yeah, you proceed in this way. The problem with uncertified DAG, and basically when Mr. Sethi was, say, implemented, they kept in mind how certified DAGs like Bullshark were implemented. They implemented precisely in this way, using pool strategy. But in the pool strategy, you have a quorum of nodes for every block who have this block in the local DAG, because you have these certificates. And it was much less problem for certified DAGs when you implement a pool strategy. Yeah, here we could have some problems with this pool strategy, and this is again, I'm sharing also some of our experience in our networks and testnet network, and also in the main network we had such kind of problem when basically if you have some slow validators who creates its blocks, every block that it creates, it's kind of like valid, but for some reason it's send these blocks, say, only to validator A. Yeah, then validator A creates its block and it references this slow chain that is not yet disseminated to anybody else. And I'm again playing for validator A, and I'm thinking, okay, let's send my block, I think it's valid, it's okay, to validator C and D. I send it, but now we are looking from the perspective of validator C. It doesn't have that slow chain of blocks from validator B. We are looking from the perspective of validator C. We received a block from validator A, and it points to some block of validator B, which is missing in our local DAG or local perception. And it takes quite some time just to retrieve all this history. Yeah, and because of exactly this effect, so we sometimes had no progress on the consensus DAG because of such slow synchronization of blocks. And let's just look at this particular problem from a more general, in a more general case, when say validator B may be connected to everybody else, but the latency between validators, they looks like that. So for instance, again, let's talk about these three validators, B, A, and C. And it could happen, and also in practice it happens, say, every day, and even right now, that for this block dissemination, we could have like a triple of validators, such that to propagate the block from B to A and from A to C, it takes less time than to propagate the same block directly from B to C. This is what we observe even now, and because of that effect, if that happens for some triple of validators, then we already decrease the number of blocks that produced, say, every second. Yeah. And for such, say, high performance consensus protocols, it's really a practical problem that for some of the connections, we don't have triangle inequality, that the sum of latency for two sides is greater than the latency for another side. And it could be not only like network problem, it could be also a software problem, because we do some throttling. Yeah, and the motivation for Starfish is that we want to mitigate this triangle inequality in the network. So we want to ensure that once you send your block, then that block can be accepted in the local DAG of the peer. And the second, and this includes, as I said, not only when we have network problems, but also when we have, say, Byzantine nodes and they send their blocks exclusively to someone else. And the second problem is that we don't want to push all the blocks, especially we don't want to push all the transaction data. Especially this problems amplifies when we have a lot of transaction data, because otherwise you consume the whole bandwidth very easily. And we want to keep the bandwidth linear with transaction data, because you want the same transaction bit to be communicated not too much, not quadratically as it was in cordial miners. And we have basically two ideas how to do it. So, and that's already implemented. So the first one is we want to decouple. So we want to split a little bit data in the block. And now we want to have a separate kind of block header, which does not include the transaction data, as you can see. And we want to push block headers instead of block. So block header contains the transaction data commitment, but it doesn't contain transaction data. And because in reality, in consensus protocols, when you do this all commit rules, sequencing of blocks, you don't care about transaction data. You only need all the ancestors, all the validness of block headers, and that's it. So, and we can push those headers because they are of more predictable size than transaction data. But the problem with block headers is that, for instance, if I have some block header, then I'm not sure that, and maybe I have transaction data, I'm not sure that the rest of the network receives the transaction data. If, say, I am the only person who receives the transaction data and others has only block headers for the same block, then they don't have transaction data. And I need a mechanism to highlight that a quorum of network knows about this transaction data. And for this purpose, we add one more, say, field in the block headers, where you need to acknowledge that the data is available on your validator. So, and then you can basically sequence the transaction data only if a quorum of the network agrees that they have the data available on their validators. Yeah, and it's the first idea. I'll then show how it's kind of like implemented. And the second idea is about how to keep the bandwidth usage linear with the transaction data to not communicate the same transactions too often. So basically what we want to do is we want to do encoding. So currently there are quite many protocols that do similar things on the kind of like network level for data propagation, but the Starfish just incorporates all these ideas in one consensus protocol. So it's this like encoding is embedded to the protocol itself, not on a separate data availability layer. So it's all embedded in the protocol. The way how we do it is as follows. So basically we have some transaction data. Then we split it into chunks, say of equal size, and we encode it using some erasure codes. So we extend the transaction data such that we have more chunks. So we had f+1 chunks and we encoded and we got n chunks. And now when you are the block creator and you're responsible for your transaction data, then you're going to send to everybody else your transaction data, while others, they should not send to everybody else the whole transaction data. They should send only one chunk, one shard, what we prove, together with some proof. Because if you receive some chunk but you don't have a proof, then we cannot employ erasure code. We need to employ some error code. And that's the basic logic. So if you are the block creator, then you're responsible for the whole transaction data. You send to everybody else the whole transaction data. But if you are not the block creator, then you're responsible for only one shard, for only one piece here. And that's what you will send to everybody else. And then in good scenario, you don't need to decode the transaction data. You don't need to do any decoding, but instead you only need to do decoding if the transaction data was not well disseminated, and then from any f+1 shards which are correct, which has valid proofs, then you can take any f+1 of those and you can get the original transaction data. Yeah, let me just probably also say how then we change the broadcast rule for own blocks. So now, when we create a block, we send to our peers not only the block itself, but also block headers of blocks of potentially missing history to all our peers together with the shards of transaction data. So now to the guy D, we send not the whole transaction data of blocks B5 and C5, but only one shard that corresponded to, say, our index. And then, yeah, okay. And now I probably can, we can look at how we can sequence the transaction data. Let's say that we are looking now at the block C1, and we are thinking when we can, say, sequence the transaction data, because we already have these acknowledgements, we have some leader blocks, how to put everything together. So basically, in, say, good case, this block is disseminated, and then in the next round or some other future rounds, you include in your block so-called, you include in the block acknowledgements, and these acknowledgements basically say the following. Okay, I received a block header from guy C1, and I have the transaction data of that block in my local validator, and now I'm going also to send my encoded shard to everyone else. That's what this acknowledgement field in the block header means. So we have a quorum of acknowledgements, and this quorum of acknowledgements about the transaction data, they all should be visible from the next leader, from some of the next leaders. So this is the pattern that we need to have on our local DAG to sequence the transaction. But the leader should be also committed using, say, previous commit rules for the leaders. So that means that for the leader, we need to have a quorum of votes. And typically, for most of the BFT protocols, you need to have not only one level of knowledge, but you need to have a second level of knowledge when we have a quorum of nodes that each of those observe another quorum of nodes voting for the leader. In this case, if you have so-called certificates on the DAG, then you can commit the leader block. In this case, you can commit the leader, and you can finally sequence the transaction. So it takes that many rounds just to commit the transaction. Okay, and let's just look also on the example why it should work. So let's say that we have an adversary here, and it sent exclusively its transaction data to some validators, but not all of them. And let's say it doesn't send it to guy B. But since we have a quorum of acknowledgements, and every honest participant who has an acknowledgement statement in the block header, it has to send its shard, its chunk of data, encoded transaction data to everybody else, we can recover the transaction data. So B can recover it because it has two shards, even though they are not like the first shards in the encoded part. We know that we used here code with some parameters, and two shards are enough to recover the original transaction data. So basically, even though the network says that we can sequence transaction data for block C1, and even though you don't receive it, you can reconstruct it by decoding. Okay, now let's take a look at the performance. So we are very close to the end. So here we checked several protocols. So we have certified and certified protocols here. So Starfish here, it's a certified DAG-based protocol, and it has the best performance among certified DAG-based protocols. And as you can see, uncertified DAG-based protocol has better performance, and particularly here, Starfish has a better performance on a very large scale, because here we do encoding, and because we can integrate blocks much faster than another protocol, Mr. SETI, which uses pool-based strategy to retrieve missing ancestors from its peers. So specifically, you can see that for low load, Starfish is worse because it requires this acknowledgement step. But for a high throughput regime, then you need you can handle a high throughput. And in some, say, attack scenarios, when we have some Byzantine validators that send the data exclusively to some to not all validators, but exclusively. So it's a specific attack which is very similar to this slow validators that send its chain of blocks exclusively to some validator. We can see that Mr. SETI doesn't have a good resilience. It has much higher latency compared to Starfish, which performance does not goes down with Byzantine validators in the network. Okay, these slides are basically explanation of this attack. Maybe we shouldn't go into these details. Yeah, I have also another comparison table between protocols in the recent years, and yeah, if you just look at this table, you can see that Starfish has a little bit larger latency than Mr. SETI, but it has better this so-called amortized communication complexity, because we do encoding for transaction data. Yeah, that's it from my side. If you have any questions, if you want to dive into some details, then you're very welcome. Yeah.
One question. You're saying that not all the validators, they have all the data, so you have only